You're working on code, you hit run, and it just sits there. Cursor blinking, loading wheels spinning. The question hits you. Is this program actually doing something? Working through a massive calculation that'll finish eventually? Or is it stuck in an infinite loop, destined to run forever, never completing? You could wait. Maybe it finishes in 5 minutes, maybe 5 hours, maybe never. Here's the uncomfortable truth. There is no algorithm, none, that can always tell you which it is. Not because we haven't built it yet, because it's impossible. Mathematically, provably, fundamentally impossible. If you're already confused, stay with me. By the end, you'll see why confusion is exactly where this story begins. In 1936, Alan Turing proved this, and in doing so, he discovered something profound about the limits of computation itself. Let's make this concrete. A program is just instructions plus input. That's it. Some programs halt. They finish and give you an answer. Some programs loop forever. They never stop running. For example, feed a simple addition program the numbers 3 and 5, and you get 8. It halts. But give that same program a question it wasn't built for, like, what's the capital of Colombia? And it doesn't fail instantly. It just keeps running, looping forever, searching for a rule that doesn't exist. The halting problem asks, can we build a program, let's call it H, that takes any program and its input, analyzes them, and tells you this will halt or this will loop forever? Seems reasonable, right? After all, you can test specific cases, run it, see what happens. But Turing asked, can you build a universal decider, one that works for every possible program? And his answer was devastating. No. Not, we haven't figured it out yet. Not, it's really hard. No, it is impossible. Here's how Turing proved it's impossible. And fair warning, this gets beautifully weird. He used a move called proof by contradiction. Assume the perfect halt checker exists, and watch how that assumption tears itself apart. Assume H exists, our perfect halt checker. You give it any program and input, and H tells you halts or loops, every time. Now, here's the twist. We build a new program, P, and inside P, we embed H. H becomes a subroutine P can call. So here's what P does. Step 1, P takes a program as input. Step 2, P asks H, if I run this program with itself as input, does it halt? Step 3, if H says yes, it halts. P deliberately loops forever. Step 4, if H says no, it loops. P immediately halts. P is designed to always do the opposite of whatever H predicts. Now, here's the problem. If H truly worked, if it could predict every program, then it should also predict the behavior of P. But the moment H makes a prediction about P, P flips it. No matter what H says, it's wrong. That's the contradiction. That's why H can't exist. This isn't a bug in our design. It's not a limitation of technology. It's a logical impossibility. Like asking for a square circle. The halting problem is undecidable. Okay, so we can't build a universal halt checker. Why does this matter? Because it means there are fundamental limits to what computers can ever do. Not practical limits, not we need better hardware limits. Fundamental, absolute, permanent. Here are real-world consequences. 1. Perfect debugging is impossible. You cannot build a program that checks any code and tells you this has no infinite loops, because that's the halting problem in disguise. 2. Perfect virus detection is impossible. A virus could be a program designed to exploit infinite loops. A perfect detector would need to solve halting. 3. Perfect optimization is impossible. Compilers can't always determine the fastest version of your code, because that requires knowing if alternative versions halt. And here's the philosophical depth. Turing didn't just limit computers. He limited any mechanical process. That includes algorithms, formal systems, even mathematical proofs. Some questions are not just hard. They're unanswerable by any systematic method. If this sounds familiar, it should. In 1931, Gödel proved that mathematics has true statements that can never be proven. In 1936, Turing proved that computation has problems that can never be solved. These aren't coincidences. They're the same idea in different domains. Both use the same trick, self-reference. Gödel. This statement cannot be proven. Turing. Does this program halt when analyzing itself? In both cases, you create something that breaks the system by pointing at itself. And what they reveal is this. Any sufficiently powerful system, whether mathematics or computation, will have limits. Edges it cannot cross. questions it cannot answer. Gödel showed math is incomplete. Turing showed computation is undecidable. And together, they painted a picture of knowledge itself. Beautiful, powerful, but fundamentally, eternally bounded. Now here's where it gets modern. You've used ChatGPT. You've seen what AI can do. It writes code, solves problems, mimics reasoning. So the question comes up, can AI bypass the halting problem? Short answer, no. Because AI, no matter how sophisticated, is still running on algorithms. And the halting problem applies to all algorithms. An AI can get really good at predicting whether specific programs halt. It can learn patterns, recognize common infinite loops, make educated guesses. But a universal solution, one that works for every possible program? Mathematically impossible. And this is important to understand as AI advances. There are problems AI will never solve. Not because it's not smart enough, not because we haven't trained it right, but because the problems themselves are unsolvable by any computational process. The halting problem is a wall that even super intelligent AI cannot break through. You might think this is depressing. Computers have limits. AI has limits. We can never know everything. But Turing didn't show us a failure. He showed us a structure, a boundary that exists not because we're not smart enough, but because logic itself has edges. We live on an island of solvability, surrounded by questions no machine can ever answer. And that isn't a flaw. It's what makes the island meaningful. Inside the limits, we can build incredible things. We just have to know where the edges are. In 1936, Turing drew a line. Decidable, undecidable. Every computer you've ever used lives on one side of that line. Powerful, but not infinite. And honestly, that's exactly as it should be. Because if machines could solve everything, there would be nothing left to wonder about. Some problems halt, some loop forever, and some we'll never know. That's not a bug, it's the design. But here's a different question. Even if a machine solves a problem, does it understand what it solved? Turing asked that too, and his answer involved a game, a conversation, and the hardest question in AI. That's a story for another time.
Drawn to philosophy.